Hi everyone. I made this video to discuss is the stationary point and how to find a stationary point, followed by what type of stationary point we have, and how do we determine which type of the stationary point we have. All right, just imagine that we have a curve like this, and you can imagine that we are driving. So when you want to make okay, you're actually driving, and then you go uh, forward by step on the accelerator. Then until you want to make a U-turn, all right, at this point you want to make a U-turn, you will step on the brake, right? So when you want to when you step on the brake, that will be a moment that you stop for a while, and we call this as a stationary point. All right, at this stationary point you can see that it has a gradient dy dx equals to 0. We know that the dy dx is representing the gradient of a point. So, or in other words, you can say that dy dx representing the gradient of a tangent at a point. For example, I call this point as a point P, and at this point we call this as a stationary point, and it has the gradient equals to 0. As you can see, that is a horizontal line if this is representing the tangent. So to get a stationary point, you just need to know the information dy dx equals to 0. From this equation, you solve, and from here you will get the point P. As an example, find the stationary point for this function. First of all, we need to find the dy dx. All right, because we know that dy dx is representing the gradient. At the stationary point, we have the gradient equals to 0. So firstly, we find the dy dx. All right, we get 3x squared minus 12x plus 9. And let the dy dx equals to 0 in order to find the stationary point. Can see that this is a quadratic equation. So we use the method solving the quadratic equation. So I would choose to factorize first. And I got this. From here we solve it. We have x equals to 1 and x equals to 3. So it means that at the stationary point, the x-coordinate of the stationary point is x equals to 1 and x equals to 3. So since the question they want the state the stationary point, meaning that we are actually concerned about the x-coordinate and the y-coordinates. So we need to further to get our y-coordinate, the corresponding y-coordinate, that is, substitute the x equals to 1 into the function to get the y value. So when I substitute the x equals to 1 into the y into the function, I got y equals to 5. That will be my first stationary point that I got, that is 1, 5. So next, we need to substitute the x equals to 3 into the function as well. And I got the y equals to 1. So that will be a 2 stationary point that I got. So make your conclusion. The stationary points are 1, 5 and 3, 1. Another example, I have function y equals to x squared minus 1, power of 1 over 3. I need to get the stationary point of this function. First of all, again, I will repeat the same method, that is finding the dy dx. For this function, I will use the power rule, means that I will differentiate the power and then as a outer layer, then multiply by differentiate the inner layer, that is your x squared minus 1. So let's differentiate the power. Differentiate the power, I got 1 over 3, bring to the front. And the power minus 1, I got a negative 2 over 3. The inner layer, just copy it back first. Multiply by, differentiate the inner layer, you got 2x. Simplify it, you will get 2x over 3 x squared minus 1 power of 2 over 3. So this represents the dy dx, that is the gradient of the curve. But I'm interested on the stationary point. So let the dy dx equals to 0, because we know at a stationary point the gradient has to be 0. So let the 2x over 3 x squared minus 1 power of 2 over 3 equals to 0. From here we solve, we have x equals to 0. So very obviously that the stationary point happen when the x equals to 0. Then if you would like to know the points, right, you need to substitute back the x equals to 0 into the y itself. So when x equals to 0, y equals to 0 square minus 1 power of 1 over 3. You will have a y equals to -1. So the stationary point is 0, -1. So next, we would like to know the stationary point that we found just now, whether it is a relative maximum point or relative minimum point. All right. We in order to determine which is which, we actually can use the first derivative test or second derivative test. For the first derivative test, if let's say that point is a relative maximum point, after we have determined the stationary point, for example, this is the stationary point that we have. We already know the point, which is its coordinates already been known, and we just need to substitute a point at the left side into the dy dx. If your dy dx shows positive, means that your y at the left hand side is increasing, and substitute again a point which is greater than our stationary point into the dy dx. If it gives you the negative value, means that your y is decreasing. So this tree line is representing the y that you have at the left side, which is increasing at the left side, and then 0 in the middle, and then decreasing at the right side. So you can see the shape is just up, 0, down. Okay, increase, and then static, and then go down. So this shape means that you are having the local maximum point, okay, at that stationary point. Another situation you have by using the first derivative test, you can test whether it is a relative minimum. Okay, for the relative minimum, you have the shape like this, the graph. So as we found the dy dx equals to 0 when you know that the stationary point happened at the x equals to c, means that you can now substitute a value which is less than the stationary point into the dy dx that you found. Then if you know that the dy dx gives you the negative value, means that at the left side, the dy dx, the y is actually decreasing. All right, and then you substitute another value which is greater than the dy dx into the a value which is greater than the stationary point into the dy dx, and it gives you the positive value, meaning that your y is increasing. So you will know that the situation is like going down at the left side, and then dy dx equals to 0 means that it's static at the middle, and then the y increasing back. You can see the pattern of the graph is actually down, static, and then up. So this representing that your shape of the graph is in this form, and you would know that the point, okay, the stationary point that you found at x equals to c is actually a relative minimum. Later on, when we answer the question by determining whether the stationary point is a maximum or minimum by using first derivative test, we are going to sketch a table, okay, to see the pattern of the graph of the function. So now we move to the second derivative test. And what does it mean by the second derivative test? Second derivative test is actually tells us whether the curve is concave up or concave down at a point. So when the dy dx gives you the d2y dx2 gives you the negative value, this means that your curve is actually concave downwards. So if let's say this is a concave downward, meaning that if your stationary point is located somewhere over here, so if the graph is concave downward, meaning that you're having the local maximum point. If your second derivative gives you the positive value, means that your graph is concave upwards. All right, so the shape is like this. If your stationary point is located over here, means that if your d2y dx2 tells you that it's concave upwards, so this point will be the local minimum point. So this method sounds easy to understand, right? So once you have the function which is easy to derive, I mean to get the second derivative, I will encourage you to use the second derivative test to test the point, the stationary point, whether it is a maximum, local maximum, or local minimum. If you realize that the second derivative of a function is hard to get, it means that the process is quite long, then I will recommend you to use the first derivative test to determine whether it is a local maximum or local minimum. Here is an example that we need to find the relative extremum points for the fx, which is a polynomial, by using the first and the second derivative test. State the interval where f is increasing or decreasing. In this case, relative extremum points means that is both is actually relative maximum and relative minimum. Both we need to find if that exists. And now we need to find the stationary point first before we proceed to the local maximum or local minimum. All right, this is the f prime x, which is the same as the dy dx. So I actually differentiate the function fx to get f prime x. And in order to get the stationary point, we will let this f prime x equals to 0 and try to factorize it and solve it. After we have factorized, here we have x equals to 0 or x equals to 2. So these two are the coordinates of the stationary point that we have, and we actually will find the corresponding y value, that is finding the f0 and f of 2. Okay, so we have 2 points. The first point, stationary point, is 0, 6, and another one is 2, 2. So in order to use the first derivative, I recommend to draw this, to sketch this table, where this line might represent the x equals to 0. All right, so you focus on these two x value, the x coordinate of the stationary point, that is 0 and 2. So of course the 0 is less than 2, so we start with the x equals to 0, and the second line is representing the x equals to 2. So for the left hand side of the 0, you might have the value which is less than 0, and in the middle, in the between 0 and 2, you have the x value which is in between 0 and 2, and at the right side of 2 you might have the x equal the value which is greater than 2. So now we need to substitute a value which is less than 0 into the f prime x, okay, to test whether the sign is positive or negative. So this is the f prime x that we have just now. Put a value which is less than 0. For example, we put a -1, okay, -1 into the f prime x, and see what we have. You got a f prime -1 is 9, means that this is having the sign of a positive. Okay, we don't care what's the value of f prime -1, but we just need to know the sign is positive, and we're going to denote to note down over here that is positive. And now is the turn to substitute the value which is in between 0 and 2. You might choose the easier value, so that when your calculation will be easy. So I'll just put a 1 into the f prime x. Here you have a negative sign. All right, -3, that is a negative sign, yeah, negative value, means that now you put in the you jot down in the table that is a negative when you will substitute a value which is in between 0 and 2 into the f prime x. So so for the following box, you need to substitute the value which is greater than 2. You can take a 2.5 or 3 into the f prime x and then calculate. So for this time, we got positive. All right. So when your f prime x is positive, means that your y is actually increasing. And so when your y is f prime x is negative, means that your y is actually decreasing. And after that, after the 2, your y increasing. All right. So when you imagine that the shape of the graph is increase, decrease, and then increase, the shape of the graph is like this. So it means that at the point x equals to 0, you are having a local maximum, and at the point x equals to 2, you will have a local minimum point. So now you can meet your conclusion. 0, 6 is a relative maximum point, and 2, 2 is a relative minimum, okay, by looking at the table. And for the increasing interval and decreasing interval, we can answer in this form. F is increasing on the interval negative infinity 0 and to infinity by looking at the interval that we state in the table. All right. And the decreasing interval is happen for the interval 0, 2. So we answer in this form. All right, now we are we're discussing about how to use a second derivative test to test whether this stationary point are local maximum or local minimum. Now, to use the second derivative test, we need to find the d2y dx2, meaning that we will differentiate one more time with respect to x from the dy dx differentiate one more time to get the 6x minus 6. Then we substitute the x equals to 0, which is the first point that we concern, x equals to 0 into the d2y dx2 we got, and it has the negative 6. It produced the value negative, means that the graph now is concave downwards. All right. So at this point 0, 6, you might see that it is actually a local maximum point. All right, so this is the conclusion that we can make for the point 0, 6. Next, we test for the second stationary point. That is when the x equals to 2. When the x equals to 2, you put the 2, substitute the 2 into the d2y dx2. It produces a value of 6, which is a positive value. Means that if d2y dx2 is positive, it represents the graph at that point is actually concave upwards. So at this point, x equals to 2, that is the point 2, 2 is a relative minimum point. This is how we determine the maximum, relative maximum point and relative minimum point by the second derivative test. All right. So for the question asking us to get the interval where f is increasing or decreasing, I recommend you use the first derivative test. It can because at the table we can see obviously at which interval it is decreasing and increasing. All right. Thank you for watching.